Hello, in this problem we are finding the work done to move an object that's attached to a string from its natural length to 6 inches beyond its natural length. So let me go ahead and start up with a solution here. That the picture is that you have, not necessarily, but I'm going to draw it such that you have a flat surface and we're just going along a straight line, and attached to something like a wall, you have an object. Now the object is being stretched out beyond its natural length. And our object is attached to a spring, and this displacement is x. So that the amount that it's stretched out beyond its natural length is x. Right, so I have this displacement is x. Now, Hooke's law says that the force required, or the force that's acting on that object when it's been stretched or compressed, is a constant k times x, and this k is a spring constant, so it depends on each spring. Now what we're going to do first in this problem is we're going to find k. Now what we're saying here is that a force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. So when x equals 4 inches, which is actually not the way I want to write it, it's a little bit of a thing here that it's not going to be 4 inches actually. I mean, it is 4 inches, but that's not the units we want to use. So it's x equals 4 inches, which is 4 inches, and then there are 1 foot in every 12 inches. So I think that's really not the most brilliant calculation I'm making here, but that's going to make 1/3 of a foot. Okay, so x is 1/3 of a foot. So what we have is that the force, a 1/3 foot, is equal to 10 pounds. In other words, then, since I have f of x equals kx, it's going to get that k times 1/3 is equal to 10, so k is equal to 30. So that's our spring constant, so f of x is equal to 30x. And now we're going to find the work done. And what is this? Okay, how much is done is to stretch it from its natural length to 6 inches beyond its natural length. So the natural length I'm going to describe as 0 feet, and then the 6 inches is equal to 6 inches times 1 foot for 12 inches, and that's 0.5 feet. So anyway, I'll just decide that 0.5, it looks fine to have that there. So I'm going to stretch this from its rest. So actually, it's attached to the wall somewhere over here, and there's a resting position. So it would sit there and not move if it's at 0 feet. That's the rest. I'm going to write x equals 0. It's not the distance from the wall where the thing is attached. So work is the integral from a to b f of x dx. And these values from x are set up so that x is the displacement from its natural length. So I need to really make that clear, because that's a sort of a tricky thing. And so x is the displacement from its natural length. So it's not the distance from the wall, the position from the wall. So the natural length of this, which is not even given where it sits at rest, the natural length is given as 0. So we integrate from 0 to 0.5, and we have 30x, and so that's, sort of an easy integral to do. So this is going to be 30x squared over 2 from 0 to 0.5, or you can put 0 to a half. So it's 15x squared. I'm gonna write this 1/2. So it's 15 1/2 squared minus 15 0 squared. I feel like my problem, or a problem, is that I'm trying to fit this into a small space. So don't do that. So this is going to give us 15 over 4, and that's pound-feet. That's what our answer should be for the work done. All right, so this problem had 2 steps. I mean, beyond just that we had to figure out what this is all about. This is problem number 7. Oh, I got it right according to the back of the book. Okay. It's problem number 7. Okay. So there's 2 parts. First of all, we're supposed to, maybe have done some background work building up to this, that Hooke's law is f of x equals kx. And what's x? X is the displacement from its natural length. That's an important thing. It's not the distance from the wall. It's the displacement from its natural length. And natural length is where where the object that's being moved would sit if it were just absolutely just fine. And there's no friction here. It just sits there, just nicely there, and it wouldn't move anywhere back and forth. There's no force applied. Okay, kx. Well, we had to find k, so that was the first step, which is done by putting x is 1/3 feet and f of x is equal to 30 pounds, 10 pounds. And so that you get 1/3 times k is 10, and then you get k is 30. Then that gives us the essential piece there that we have now the function f of x. Now, I have a pretty messy picture here, but I'm looking at the work done where we're moving from 0 being the resting place to 0.5 being the, just some other place. And I just thought I'd try to somehow improve this picture. Maybe I think the thing is to draw my spring in a different way. I've seen springs done like this instead of that little spiral. So we're going from 0 to 0.5. Work is given by this formula. Work is the integral from a to b f of x dx, where x equals a and x equals b are the distance from a resting position. So I have 0 to 0.5, and then you integrate, and that's sort of easy. Okay, so that finishes this video.